And thanks very much for the invitation and the opportunity to speak here. Okay, so I should start by telling you what is the Hasse norm principle. I said it throughout the talk. L over K is a finite. Well, okay, it's an extension of number fields. I guess I didn't need to say it was finite if they're both number fields. And so we have the usual norm map from Galois theory from L down to K, and it's a homomorphism on the multiplicative groups. And then we can embed L star into its ideals. Okay. Isn't it? And the same down here. And the norm map extends to the norm map on the ideals explicitly. What does it do? The entry and place V downstairs is the product of all the places lying above V. Places of W, take the local norms, the elements upstairs. So this diagram commutes. And so in particular, if I have an element of K, which is in the image of this norm map, then when I view it as an ideal, it's the norm of some ideal. The obvious one. The question is, what about going the other way? What if I have an element in K, which when I view it as an ideal, is in the image of this idelic norm map? So it's a norm everywhere locally. Does that mean it actually has to be a norm from L? We can define the knot group attached to this extension as the thing that measures the failure of this local global principle. It is actually a Tate-Shafrabish group of a non-one torus. It's a geometric way to interpret Hasse norm principle stuff, but I'm not going to go into that. Okay, so since this diagram commutes, we have this, we can form this quotient group, and we say that the Hasse norm principle holds if this group is trivial. So if being an everywhere local norm is equivalent to being a global norm from this extension. So I'll abbreviate Hasse norm principle as HMP.
Why do they call them the knot group? Does it have something to do? There's some analog in topology? Or?
No, I don't think it's a topology thing. At least, so I can't remember. Somebody told me recently.
Yeah, I guess it's a German thermodynamic, and so I guess the people who worked on this at the time thought that it was something difficult.
Yeah,
Schulze.
it's the Gordian knot.
The terminology comes from Schulze.
Yeah,
I think it.
German.
Yeah,
like a knot, like an obstruction.
yeah, like the
Idea of
Gordian knot from some classical
Okay, all right.
stories.
Something
So something that gets in the way.
Something that's annoying, yes.
It's annoying, yeah.
Yeah, that you wish you weren't there.
I mean, the Russian authors with the total obstruction to the Hasse norm principle, which is very descriptive but quite long.
Yeah.
But certainly when you try to find out why it's called the knot group, when you look up knots and number fields, you get all this much more modern stuff about topology, and that's not the etymology. Okay. So it's trivial when we say that the principle holds. So for example, we have some very sufficient conditions for it holding. So the original Hasse norm theorem says that it holds for Galois extensions with cyclic Galois group. We also know it holds for extensions of prime degree as a result of Bartos. And then you take an extension of degree n, and you ask the normal closure of this extension as Galois group dihedral of order 2n. And the Hasse norm principle holds by Bartels. Sa, and it holds by the result of Konievsky. And if it's an and not equal, then it holds by a result of Sa. All its conditions mean that, the smallest example in which you could have a failure is, well, it holds for prime degree and it holds for cyclic extension, so it's got to be degree 4 at least, and it can't be cyclic or dihedral or any of these other groups. So quadratic extensions are the first case where you can hope for failure. And in Hasse's original paper, it was called a theorem and a counterexample. He gave this counterexample for the Hasse norm principle. This biquadratic extension, root minus 2 and root 13. So in this case, 3 is a counterexample. So 3 is everywhere locally a norm, but not a global in this extension. And so the question I want to talk about today is, like, how frequent are these failures? How hard do you have to work to find one? And there are two ways, or at least two ways, to interpret this question. So the first interpretation, which is the easier one, is like if you fetch an extension, like for example this one, like you could ask, well, how many rational numbers are counterexamples to the Hasse principle? So you can fix your extension and count counterexamples. You're counting numbers in K, which are everywhere locally norms, delic norms, but not global norms. The other variant, the other interpretation of this question is, like, suppose I fix a base field like the rationals. Maybe I want to know, like, for how many biquadratic extensions the rationals failed that the Hasse norm principle. It's K and the L vary in some family. E.g. Q biquadratic. And we count L with non-trivial not. So regarding the first interpretation, this the base field in rationals, this is something I studied with Tim Browning. So, okay, we want to count rational numbers that are sorry, L equals Q, no, L over Q. Fix an extension L over the rationals, and I want to count rational numbers. Well, let's count the ones that are everyone local norms. up to some height. So, height, the usual height of a rational number. It's the maximum. Numerator and denominator. So write it in lowest common terms. All right. So then let's compare this to the global norms. And then the counter examples, of course, are just going to be the local norms, which are not global norms. The result that we got is kind of the thing we hope is going to be true. We're counting the proportion of we're counting the counter examples as a proportion of the everywhere local norms. By the way, I mean, already everywhere local norms are like 0% of rational numbers. That's why we do this. And we get just what you hope to be true. So 1 minus 1 over the size of the norm group. So in other words, the global norms as a proportion of the local norms are 1 over the size of the knot group, which is what you want to be true because there's one trivial element in your group. So this is just saying that this all behaves nicely with respect to the height on rational. Okay, so for the rest of the talk, I'm going to focus on 2.
Do you actually prove that the rational points are equidistributed and then not grouped? That the locally, I mean.
So we give asymptotic formula
Locally solvable ones, yeah.
we give an asymptotic formula for this one, and then we actually give an asymptotic formula for this one, and there's some just the constants that come up differ by one of the sides of the knot group, and that comes from work of Adoni and class field theory.
Okay, I'm just asking, is the stronger statement true that
I don't know.
all ones are
Yeah, I don't.
distributed among the
I
class?
haven't thought about that.
Okay.
Thought about that
So
question.
it seems likely that your methods would probably give that as well.
Maybe, yeah,
Okay.
but I haven't thought about it. Okay.
You said there was some big relation to SHA of a norm 1 torus, and I remember that there's a relation of class groups.
Equality.
Yeah.
It's not a
Okay.
big relation.
So then
The
there's
knot group is
okay.
the Tate-Shafarevich of the group of the associated with the
So I think class groups are related to like Selmer groups of norm 1 tori. Do you know if there's a relation of these to class groups or torus class groups?
I don't know about that, and I would love to talk to you about it afterwards.
Sure.
That would be great. Okay, so let me focus on fixing K and varying L. So what do we know in the case of abelian extensions? Well, for example, let's look at a simple biquadratic case. So let's build a biquadratic extension. So let me take simplicity. A and B are going to be integers, they're co-prime, they're going to be square free, and to not worry about conditions at 2, let's make them both 1 4. Then we have a very nice to write down condition for when the Hasse norm principle fails for the biquadratic extension, where we adjoin the square roots of A and B to the rationals. So it fails if and only if A is a square mod P, for all times P dividing B, and B is a square mod P, for all times P dividing A. So this is something that probably wouldn't just happen by coincidence, and this kind of gives the idea that probably 0% of biquadratic extensions fail the Hasse principle when ordered by discriminant, for example. Okay, so with Frey-Lachlan, we proved a certain more general result. So instead of just dealing with biquadratics, we took G to be non-trivial, otherwise there's not much counting to do. G is going to be our Galois group file extension. Non-trivial finite abelian group. And let Q be the smallest prime. Dividing the order of J. And suppose that if I quotient G by it's a Q torsion subgroup, and I get something cyclic. So, I mean, in the biquadratic case, Q would be true, and this would be trivial. Certainly cyclic. Then 100% of what we call G extension, right? Meaning Galois extensions with Galois group G, satisfy that's a norm principle when ordered by discriminant. So of course, if I'm going to count number fields, I have to order them as well. Let me just write G extension. Okay, is a Galois. Okay, with Galois group. To G. So this is a qualitative result. Nick Rome in 2018, we looked at the biquadratic case. You can really like parameterize these extensions in a nice way, and he gave an asymptotic formula for the number of biquadratics. So biquadratics over the rationals for the Hasse principle. And therefore he recovered our result in the biquadratic case. But obviously, like an asymptotic formula is much better than just like, I mean, our result is like 0%. Okay. And then, so I put some condition on the group, right? So what about the other case? Well, yeah, it is really a dichotomy. So when you order by discriminant, if your group doesn't have this kind of shape, but when you quotient by the Q torsion subgroup, you get something cyclic, then you can get a positive, then you do get a positive proportion of failures. So let me so this is attribute this to Koymans and Rome this year, like building on. So it's like their results kind of an improvement of our result, which was in the same paper. So I'm going to say did I number that theorem? Theorem 2, good. A G and Q being theorem 2, except that let's suppose that this is not cyclic. So, I mean, just G is a non-trivial finite abelian group and Q is the smallest prime dividing the order of G, but I don't want this now to be cyclic. Then this the proportion of G extensions K is satisfying the Hasse principle. So ordered by discriminant, ordered by the absolute norm of the relative discriminant. So we want to do a proportion over the total number G extensions ordered by, rewrite it properly, G extension ordered by discriminant bounded by X. So this limit is strictly between 0 and 1. So that means that there's a positive proportion of failures and a positive proportion of successes. And what about asymptotic formulae? Well, in the case where, let me be careful to get this right. So we've got all these products of cyclic groups of prime order. So one is the smallest one, these primes. And like most of these exponents are just one. So this product is 2. So one of these is 2 and 1, and all the rest are 1. I mean, if they're all 1, then it's just cyclic groups. We know that the Hasse principle always holds. So in this setting, Clemens and Rome did give asymptotic formula. That was in 2022. They gave asymptotic formula for number of G extensions Q. So yeah, only over the rationals failing. That's an principle. But the ordering here turns out to be very important. So like when Chris and Dan and I obtained this result, like we were very surprised actually. Like our default assumption, I guess just inspired by the biquadratic case, was that for abelian extensions we would expect the Hasse principle to hold 100% of the time, but we got positive proportion failures in these cases. But it turns out that it's like sensitive to the ordering. So in later work where we were studying abelian extensions with prescribed norms, so again, G is a finite abelian. I don't need to say non-trivial. It's not really interesting if it's trivial. 100, like if you order instead by, if you order your abelian extensions by conductor rather than discriminant, you actually find that 100%. the extensions of K is assumed to be fixed throughout. It's in the field. Satisfy the Hasse norm principle and ordered by conductor. So maybe that you should really order your abelian extensions by conductor and get the result that I think should be true. So that's all I want to say about abelian extensions. And like when I was giving talks about this work, of course, the question I always get is, what about non-abelian extensions? I mean, and those are like, there's not that many families in which we can count and where the Hasse norm principle can potentially fail. Right? It holds for all cubics, for example, like the results that I stated at the beginning. So, like, first was to find some families where people write the patterns. Okay. Considering his thesis in 21, did the first non-abelian counting result, and he showed that 100% of default octets, so Galois degree 8 extensions with a dihedral Galois group, satisfy Hasse norm principle. And it didn't matter in this case what the ordering was. And ordered by either discriminant or, well, let's say by conductor, but I should be more precise. What do I mean by conductor in this setting? So by Artin conductor of two-dimensional, irreducible, faithful representation of D4. Okay, and so the counting, the hard work was done. Like the counting work was done by the following authors. And I meant to ask a rule in the break how to pronounce the name of this author. I'm going to say Altuk, but I don't know. So in 2021, they counted D4 optics ordered by this Artin. Well, they counted D4 cortex. Optics ordered by this Artin conductor of this two-dimensional representation. And the fourth palming work, Shankar and Varma, to count D4 optics or cortex by generally, the discriminant counts are much harder and not as nice to work with. And I think that probably comes down to the Melanie Matchwood's philosophy of fair counting function. Like when you have a fair counting function like an Artin conductor, then you get very nice Euler product formulae with local conditions at all places. And that's very good for us. Okay, so in work which is almost done with the Varma, so I kind of hoped to get this on the archive in time for this conference, but it didn't quite happen. So what's another family in which we can count number fields? So S4 extensions. So that D be either 8 or 24. The Hasse norm principle holds for 100% of S4 extensions of degree D of our fixed number. Okay. How are we ordering? When ordered by art and conductor of standard representation of S4. So this is a faithful three-dimensional representation. And so, yeah, I mean, by an S4 extension of degree D, I mean extension of degree D whose normal closure has Galois group S4. Okay, so, and we have similar results for then S5 extensions. So, so this builds on previous work with Andre Macedo. In 2022, he gave formulae and explicit methods for computing knot groups. Well, we had some more general theoretical results, but particularly the results are optimized for AN and SN extensions of any degree.
About theorem 6 in the degree 8 case, is it true that 100% of the extensions are dihedral D4 extensions? Or,
Oh.
I mean sorry, not, oh no, sorry, doesn't make sense.
I'm restricting myself
Sorry.
to S4. I'm not counting within families of all degree 8 extensions. Although
Okay, never mind.
in this
I
work,
misread the.
in this work with Macedo, we give some conditional results conditional on Malus conjecture for families where you just restrict to 1 degree, but you don't care what the Galois group is. So we have some results in that direction, but they're conditional results.
Why 8 and 24?
Yeah, but this comes out of this formula. So let me just finish what I was saying here. So when I say AN and SN extensions, I mean of any degree. So like in particular, not necessarily Galois. I mean, computing knot groups in the Galois cases, it's much easier. And in the case, like you could do this in any case that you wanted to do, but it becomes messy. Let me say criteria for failure of as a norm principle for NS4 and 5, because like I knew that I wanted to do this work with ELA with for S4 and S5 extensions, and so we wanted like explicit criteria that we could work with. So the criteria are in terms of like local decomposition groups. So let me, so in particular, like showed in the paper with Andre Macedo that like we were able to determine exactly which S4 extensions could possibly fail. That's a norm principle. So apart from degrees 8 and 24, the only other types of S4 extensions where you can get a failure, right, can fail, are degree 12 fixed by, so degree 12 extension. So you have a Galois extension with Galois group S4, right? So it's degree 24. And I'm saying a degree 12 extension inside this, but a degree 12 extension that's fixed by something of order 2. But in S4, I have 2 flavors of elements of order 2, so kind of single transpositions and double transpositions. And so the ones that can fail are the ones fixed by a double transposition. So, I mean, like, we know already from the results earlier that like S4 cortex, they can't fail the Hasse norm principle. Something of degree n with Galois group Sn by the result of Kunyavsi can't fail. And we just give the criteria for failure. In particular, we say which ones can fail, and then we give the local condition. So then what about these degree 12 guys?
They actually can fail, so there are counterexamples.
Yeah.
in this degree. Okay.
Yes. Yeah, they actually can fail. You just have to, so in fact, in the paper, we give explicit examples. Andre Marcelo found explicit examples to demonstrate failure in every situation where it could potentially happen. Yeah, so thanks for the question. Yeah, that's important. And then once you have a failure, I think you'll have infinitely many, because you can just find some family that like kind of locally at the places which are important. Okay. Fixed by double transposition. So let me call that family. I'll just call it F12. In Obama and we give asymptotic formula for the number of fields in this F12 family failing the Hasse norm principle, and in particular shows they represent a positive proportion of the total number of fields in F12. Okay. Ordered by art and conductor. Art and conductor of the standard representation.
What would the formula for the AN and SN extensions depend on?
Local, yeah, I'll
Oh.
give an example, but yeah, it's just the local decomposition groups at the ramified pipes. Maybe I'll do that now. I was going to do that a little later, but I might as well just do that now. So like, I'll just give an example, but so for example, Hasse norm principle fails for one of these F12 fields. We can only if four times P of K decomposition group doesn't contain a kind of normal copy of V4 inside S4. So, this is actually extremely similar to this condition. This is all about, this is asking about whether you have a local decomposition group, which is V4. So yeah, this is the decomposition group this is normal closure. So these local conditions just depend on decomposition groups in the normal closure. I kind of forgot when I started, so I don't remember.
40 minutes.
Okay, great. So. And let me just say that we have completely analogous results for S5. We can classify exactly which ones fail, and we can count, and we either show 0% or we give a percentage. So for these results, we use counting result due to Vargava, Shankar. Well, this is a very nice counting result. It allows you to impose local conditions. So for place P, okay, sigma P, the set of isomorphism classes. Yeah, I'm just going to do I'm going to stick to S4 case, but everything works for S5 case, which would correspond to quintic étale algebras. But here it's isomorphism classes of quartic étale algebras over the completion of K. Okay? And then we write sigma for the collection of all of these sigma P's. So this is going to be a collection of local conditions, because we're going to say that like the completion of our number field has to lie in this set sigma P for all P. So this is an acceptable set of local conditions if all but finitely many primes we allow all quartic étale algebras that aren't kind of too badly sorry, it contains all quartic étale algebras over P that have square free relative discriminant. Okay, and now we want to count, or we want to count with these local conditions. So counting function of the number of isomorphism classes of quartics to the quartic fields. I'll explain the relation between this is what I want to count in a second. Quartic S4 extensions with discriminant or absolute norm of the relative discriminant at most of x. I'm just like putting all the notation in place in order to be able to state the counting result that I want to use from Vargava work. So suppose that your collection of local conditions is acceptable, then the proportion, well, no, I guess it's not stated as proportion, but you can easily compare this to the total count. So let me just say that you divide the number of extensions satisfying these local conditions by and bounded indiscriminate by x. multiply that by X, then we get this very nice formula. Here we have a product of local masses. So these were the local masses that Sebastian spoke about in his talk yesterday. I've noticed that I stopped writing in Delta, I wrote this. It's still this. So this is for finite primes and for infinite primes. Simple, just 1 over the number of automorphisms. And they also give a nice formula for these local masses when sigma p is just the set of, you allow everything. All,
What is the date of this? Is it a recent result or? Because you didn't.
Definition that you just covered, yeah, sorry.
Theorem 7, so.
The
what
year for
is
theorem
the year
7.
of this?
oh, well, what's the because I can only find the archive version. So I should put the date that went up in the archive, I guess, but I don't know. That's about
Roughly speaking.
2016. Yeah, thanks. Oh, okay. So I shouldn't have, but I should put 2016.
There's no sigma in your definition of n sigma.
Oh, thank you. Yeah. Okay. Brilliant. That's it. Well, it's good that there was kind of a space here. It's in the wrong place. That's that. Such that. Let me put it. How about this? Such that. I want all the completions. Like so for P, I want LP to be in the set sigma P of extensions allowed at P. Thank you very much for pointing that out. All right. So now, probably I'm almost out of time now. I had to relate this to like what we're actually doing. Because this is counting cortex by discriminant. I said I want to count things like, I know, things in F12 or optics or something. That was a bad job. Maybe I already used it. No, it's there. Thank you. So, ordering. Okay, so this is my situation. Here's my extension. This is an S4. Oh, no, this is their extension. This is their S4 quartet. This some copy of S3 is fixing this. This is in the counted quartet set. But then the conductive discriminant formula tells you that the discriminant of K is the Artin conductor of the induced representation. Induce the trivial representation from S3, which is fixing you out of S4. And when we do this, we get a copy of the trivial representation plus the standard representation. You can take that to be the definition of the standard representation. It's just from the action on the cosets. Okay. And so the upshot of this is that counting our families, counting within our families of S4 extensions ordered by the Artin conductor of the standard representation is equivalent to counting families of S4 cortex ordered by discriminant. And there isn't really anything going on here. I'm just saying that, like, you know, if I have, say, an S4 optic, well, then, you know, inside its normal closure, there's the isomorphism class of a quartic. And yeah, so that's the correspondence that you can use. And this counting by the standard representation is it's kind of cheating, really. It's just then we get to count cortex by discriminant, and we can apply these counting results.
The standard means it's the three-dimensional representation of S4, like the sum 0, like x1 sum 0. Okay.
Yeah. Okay. I already told you the local conditions. And so let me go back to them though. So we want to apply the result. We have to show that this collection of conditions is acceptable. So in the S12 case, this is the condition we get, and it's acceptable. So let me just say, for example, like what kind of étale algebras am I counting here? So let me just do a simple case. If the norm of my prime is 1 mod 4, then I'm just, the ones I want to count, the complement of this single biquadratic extension. So this is, I mean, I guess this is the only biquadratic extension. This is, we're taking the square root of uniformizer and square root of something that generates FP star mod squares. Okay, and this has discriminant squared. I mean, strictly speaking, it's ideal, right? So this is something we're allowed to exclude at every place. Like the definition of being acceptable, which is probably obscured. Yeah, so, and if the norm is 3 mod 4, we just have to exclude like one more extension or one more family of extensions, not bad. When P lies above 2, we need to, well, there's a couple of things we need to exclude, but then we have to throw back in the C4 extensions. Yeah, local extensions with the Galois group cyclic of order 4, and computing that mass is hard. And that's what Sebastian has done and what he presented yesterday. So that was like the missing piece for getting our result here. So, oh, and let me say, sorry, one more remark. So I talked here about, well, I said everything's acceptable for, say, the optics, where we're going to get a 0% result. So in that case, we have to exclude yeah, all copies of V4, and it's not acceptable anymore. But of course, we just lower our expectations, and we just say we just want to get a 0% result. So we're always allowed to impose finitely many local conditions, because acceptable is something for all but finitely many. So we impose finitely many local conditions, like we exclude these decomposition groups, finitely many local conditions. at finite many places, and then we let that number of places grow, and we show that this thing in limit will give 0%. Okay, I'm slightly over time. Thanks very much for your patience.